So in today's video, we're going to go ahead and look at how we can represent left and right Riemann sums by using summation notation or sigma notation. And so here we have two general formulas. So whenever we have a left Riemann sum, and this left Riemann sum has to be uniform with n subdivisions, then the general formula to represent this Riemann sum in sigma notation is going to be the sum from I equals 0 to n minus 1 of delta x times f of x sub I. And we're going to see what these different variables mean in a second. And then for a right Riemann sum, again with n subdivisions that are all uniform, we have the formula as the sum from I equals 1 to n of delta x times f of x sub I. And keep in mind here, the only difference really is just the indices. So here we have, for a right Riemann sum, we have the sum from I equals 1 to n. For a left Riemann sum, we have the sum from I equals 0 to n minus 1. So that's really all you need to remember, because these, two portions, these arguments, I guess, are basically the same. And so the variables that we're defining over here, so n, as I mentioned, is the number of subdivisions that we have over our finite interval from a to b, right? And then delta x is essentially just the kind of difference, the endpoint of our interval minus the beginning point. So b minus a divided by the number of subdivisions we have. So delta x is b minus a over n. And then over here, x sub I, this is kind of just a dummy variable, is equal to the value of the x value at the beginning of our interval, so a, plus some variable I times delta x, and delta x is as we defined it right over here. And so those are all the variables defined. We're going to see now what this actually means. So here's a particular function. Let's look at f of x equals to x squared. And let's say we wanted to determine, using a left Riemann sum approximation, the definite integral from positive 1, so from x equals positive 1 to 3. So let me mark this interval out right over here. Okay, should look something like that. So this is the interval. We want to find the area under the curve. We want to find this area right over here. And so in order to do that, what we can do is we can use a left Riemann sum approximation, or we can use a right Riemann sum, either one. And in fact, let's actually use a right Riemann sum. It may be a little bit better because this function is an increasing function. And so what we want to do is we want to use a right Riemann sum, and let's say we want to use 4 subdivisions. So let me fix this line first of all. I don't know why it came out like that. Okay, whatever. And let's say we want to use 4 equal subdivisions. So we can divide this interval up into 4 parts. So how would we do that? How would we determine what the length of each subinterval should be? Well, if we want it to be in 4 equal parts, we're using 4 equal subdivisions, then we can just determine that the length, so first of all, if we want to find the length of each subinterval, then we'd have to take the length of the entire interval and then divide it by the number of subdivisions we want. And that is exactly what delta x is. So in this case, delta x would be equal to 3 minus 1, which is the length of the subinterval. It's this entire length right over here, and then divided by the number of subdivisions we want over our interval. So we want 4 equal subdivisions, so that's 2 over 4, which is equal to 0.5. So that's the length of each subinterval or subdivision, if you will. So let's go ahead and, let's go ahead and represent that. So this would be our first kind of subdivision. This is our second one. And then this one would be our third. And then that would be our 4 subintervals right over there. And now the next thing we want to do is we want to use the right Riemann sum. And so what we're going to do is we're going to use the value of the function evaluated on the right-hand side of each interval. So let's go ahead and represent that. So let's go ahead and show what that would look like. So this is the first Riemann sum. And then this one right over here is the second one. This is the third one. And then this one right over here would be the final one. Let me fix that. So this is the fourth Riemann sum right over here. We're using a right Riemann sum approximation. And so how could we actually represent that in terms of an equation? So basically, we're starting off at x equals 1, and what we're doing is each time we're adding 0.5. We're adding our delta x to our x value right over there. So for example, for our first subdivision right over here, this one, let's say that this area is A1, right? Essentially what we can say is A1 is going to be, the area of A1 is going to be the base, right? The base length, which is delta x, which is 0.5. And we're going to multiply that by the height. But what is the height? The height is the function evaluated So it's going to be f of essentially the right-hand side of our interval, which is going to be, in this case, it's going to be 1 plus 0.5, right? Because we have right over here 1.5, because we're increasing by 0.5 for each individual subinterval. And then if we want to look at this next area, we can call this one right over here A2. Then this one would be represented by, again, the area would be the base length, which is 0.5, times f of, so times the function evaluated at the left-hand side, which is just going to be the left-hand side of this subinterval, which is f of 2. And essentially, that is just the previous interval plus delta x, right? So that's the previous kind of portion or subdivision marker, I guess, plus the increment, right? So plus 0.5. And then we can do that for A3 as well and A4. So let me just go through this very quickly. So this would be A3, this would be A4. And then again, A3 would be the area, A3 would be 0.5, the base, times essentially just the left-hand side, right, of our subdivision plus our increment. So 2 plus 0.5. And then the same idea applies to A4. So it would be 0.5 times f of 2.5 plus 0.5. And that would be your total area. Now, how can we kind of generalize this notion? Well, it seems like each time for our right-Riemann sum, we're essentially, for the height of the function, we're just taking the value of, or the x value at the left-hand side of our subinterval, and we're just adding it to the increment, right, to delta x. So in general, we can say that a sub I is going to be equal to delta x times f of, this is going to be, what is this going to be? This is going to be the first portion of our interval, right? The first kind of beginning point of our interval. So it's going to be a, that's going to be a plus, we're adding delta x, right? We're adding delta x every time, and we're just adding integer multiples of delta x. So this one right over here, this would be kind of, this would be our beginning point, a plus 0.5 times 1, or delta x times 1. This one would be, again, this one would be 1 plus 0.5 plus 0.5, which is 2 times 0.5. This one would be 1 plus 3 times 0.5. 1 plus 4 times 0.5. And so essentially each time we're adding just integer multiples of our increment, right? So this is going to be delta x times our variable I. So that is where we get this kind of general formula. If we want to find the entire area, then we would sum it up. And I'll leave it to you to figure out why we have to use these different indices. And I want you just to think about where we're starting, which kind of, if we're starting at the left-hand side or at the right-hand side of each individual subinterval, and see why we end up with two different indices for when we are dealing with a left Riemann sum and a right Riemann sum. So I hope this kind of provides you with the intuition of these formulas. It's very helpful to know these formulas, and you don't really need to memorize them because it's quite easy to derive when you just think about it. Draw out a general or an arbitrary example and then try to generalize it that way.